Dear students, this video I explain two important things. First one is comparison of two integrals. Next is practical comparison test. Practical comparison test is to solve the problems. So far in the previous videos I explained what is an improper integral, different types of improper integrals, and when we say that improper integral converges, and how to test the convergence of improper integrals using the definition. In all that problems, primitives were easy to obtain. We can easily integrate. But sometimes what happens? It is difficult to obtain the primitive. In such cases, we require certain tests, and we consider that one now. And in the previous video, I explained what is the necessary and sufficient condition. Necessary and sufficient condition. Sufficient condition for the convergence of improper integral. What is that? The necessary and sufficient condition for improper integral a to b fx dx to converge at a is that there exists a positive integer k, so that a plus epsilon to b fx dx is less than k. That means necessary and sufficient condition for a to b fx dx to converge is that a plus epsilon to b fx dx is less than k. That means a plus epsilon to b fx dx must be bounded. This is very important. This is the necessary and sufficient condition for improper integral to converge. Now, based on this, we prove first this one. What is the test? Comparison of two integrals. Suppose f and pi be two functions such that both are positive in AB, and fx is less than or equal to pi x. This is important. Fx is less than or equal to pi x. Then what happens? Test says this: a to b pi x dx converge implies a to b fx dx also converge. A to b fx dx does not converge implies a to b pi x dx also does not converge. Now proof is based on the necessary and sufficient condition. Now what is given here? Proof is like this. Proof is, it is directly based on necessary and sufficient condition. What is the necessary and sufficient condition? Necessary and sufficient condition is a to b fx dx converge implies that a to b fx dx must be bounded. Using that we can easily prove this. Now proof is like this. What is given here? Fx and pi x are both positive. Both are positive for all x belongs to AB. This is given. And what is first one? First one, let a to b pi x dx converge. A to b pi x dx converge. Now this implies a to b pi x dx converge. What is given? Fx is less than or equal to pi x. A to b fx a to b pi x dx converge at a. This implies a plus epsilon to b pi x dx is less than or equal to k. There exists a positive real number k. Positive real number k. For positive real number k, a plus epsilon to b pi x dx is less than or equal to k. Now, this implies a to b fx dx pi x dx less than or equal to k implies, since here, what is given? Since fx is less than or equal to pi x, less than or equal to pi x, a plus epsilon to b fx dx less than or equal to a plus epsilon to b pi x dx. In inequality of integrals, we have proved this one. While studying Riemann integration, we have studied this one. If fx is less than or equal to pi x, a to b fx dx is less than or equal to a to b pi x dx. Now, since this is less than k, this implies a plus epsilon to b fx dx is less than or equal to k. This implies a to b fx dx converge. A to b fx dx converge. Now the second case is, what is the second one? Second is a to b fx dx does not converge. Suppose a to b fx dx does not converge. Does not converge. Converge at a here. What does this imply? A to b fx dx does not converge means it is not bounded by necessary and sufficient conditions of convergence. This implies a plus epsilon to b fx dx is not bounded. Not bounded. Since pi x is greater than or equal to fx, integral a plus epsilon to b pi x dx is greater than or equal to a plus epsilon to b fx dx. Since this a plus epsilon to b fx dx is not bounded, and from this a plus epsilon to b pi x dx is not bounded. Not bounded. What does this imply? A plus epsilon to b pi x dx does not converge. Does not converge. See, all the proof depends on only that necessary and sufficient conditions of convergence. Necessary and sufficient condition for convergence. And the one more thing is, we have taken only the positive integrals. Positive integrals. Next is practical comparison test. Practical comparison test. So what does test says here? Suppose fx and pi x are both positive in closed interval AB, and limit fx by pi x as x tends to a is equal to L. Then what happens? L is also positive because both fx and pi x are positive. Fx and pi x are both positive. Limit fx by pi x extends to a is L. If L is not zero and finite, then integral a to b fx dx and a to b pi of x dx either both converge or do not converge. Both converge or do not converge. This is the practical comparison test. It is called practical comparison test as it is applicable to problems, because the previous one cannot be used for problems. All the problems it is difficult to solve by using previous test. So this test is for solve the problems. Therefore, it is called practical comparison test. How to prove this one? Proof of this. Now here, to prove this, I explain one important thing here. Important thing means, suppose A is the only point of infinite discontinuity of fx dx, then we write a plus epsilon to b fx dx is a plus epsilon to c fx dx plus c to b fx dx. Suppose a is the only point of infinite discontinuity, then when we say that a to b fx dx converge, if limit a plus epsilon to b fx dx exists, and suppose c is very near to a, c is near to a, we write a plus epsilon to b fx dx as a plus epsilon to c plus c to b. C is very near to b, c is very near to a. Then a plus epsilon to c fx dx and c to b fx dx either both converge or both do not converge. Try to understand. We have written a plus epsilon to b as a plus epsilon to c plus c to b. What is c? C is greater than a, less than b, and c is near to a here. Near to a. Why we consider this is to consider a plus epsilon to c is easy and simple than to consider a plus epsilon to b. To consider a plus epsilon to c is easier and simple. So we write a plus epsilon to b fx dx as a plus epsilon to c fx dx, c to b fx dx. And these two, a plus epsilon to c and c to b, either both converge or both do not converge. Now we use this in the proof of practical comparison test. Now to prove the theorem, this practical comparison test, what is given? Limit fx by pi x as x tends to a is equal to L. Therefore L is positive here. Why L is positive? L is positive because this both fx and pi x are positive. What does this imply? This implies there exists delta greater than 0 such that L minus delta less than or equal to fx by pi x less than or equal to L plus delta. Correct? Where a less than or equal to x less than c. We consider a is the distant point of discontinuity. We consider a small neighborhood of a, and for x greater than or equal to a less than c, this fx by pi x by definition of limit greater than or equal to L minus delta less than or equal to L plus delta. Now this implies L minus delta into pi x less than or equal to fx, and fx is less than or equal to L plus delta into pi of x, where for all x belongs to AC. For all x belongs to AC. I think this step is clear for all of you. I have used the definition of limit here. What is the definition of limit? Limit is L means there exists delta, so that fx by pi x lies between L minus delta and L plus delta. From that we can write this one. Fx is less than or equal to, take this as 1, this as 2. Now suppose fx dx converge. First we take integral a to b fx dx converge. A to b fx dx converge. This implies integral a to c fx dx also converge. Now from 1 L minus integral a to c L minus delta pi x dx converge. See, we have used the previous test here. See here, from 1 L minus delta pi x is less than or equal to fx. This fx a to c fx dx converge implies a to c L minus delta pi x dx also converge. This implies a to c pi x dx converge. A to c pi x dx converge. This implies a to b pi x dx converge. Pi x dx converge. Therefore, a to b fx dx converge implies a to b pi x dx converge. Now, next thing is, we assume that what we have taken first, a to b fx dx converge implies a to b pi x dx converge. Now suppose a to b pi x dx does not converge. We are using one here, does not converge. This implies a to c pi x dx does not converge. This implies a to c L minus delta pi x dx does not converge. This implies a to c fx dx does not converge. What is the reason? Because from 1. Now this implies a to c fx dx does not converge implies a to b fx dx also does not converge. Therefore, a to b fx dx converge implies a to b pi x dx converge. A to b pi x dx converge, and a to b pi x dx does not converge implies a to b fx dx also does not converge. Now similarly from 2 we can prove that if a to b pi x dx converge, then a to b fx dx converge. From 2. From 1 what we have proved? A to b fx dx converge implies a to b pi x dx converge. From 2 we prove that a to b pi x dx converge implies a to b fx dx converge. Similarly, a to b pi x dx, a to b fx dx does not converge implies a to b pi x dx also does not converge. From 2 we can prove this one. So we either both this a to b fx dx and a to b pi x dx either both converge or both do not converge. Why we have taken here a to b fx dx converge implies a to c fx dx also converge? Because we have taken a point in between a and b, and to consider a to c fx dx is easier and simple than a to b fx dx. That is the only reason. As explained in the note, you go through that note and you can easily understand the proof of this one. So finally, what does practical comparison test says? If fx and pi x are both positive and limit fx by pi x is real, fx by pi x is real, then integral a to b fx dx and a to b pi x dx either both converge or both do not converge. This is the comparison test. Using this comparison test, we can solve many problems. What is the theorem? theorem is like this. First we have taken a to b fx dx converge implies a to b pi x dx converge. For that we have used 1. From 2, if a to b pi x dx converge, then a to b fx dx converge. And similarly, using 2, if a to b pi fx dx does not converge, then a to b pi x dx does not converge. So both these two either converge or does not converge if this is the condition. Fx by pi x is yeah. Now I explain how to apply this for problems. I consider some problems and taking problems I explain how to apply this. And proof of the theorem is also important from a point of view of examination, because in the examination you may get the proof of this. Try to understand the proof. If you have any difficulties, you can contact at any time. Now, how to apply this? We require one more integral here to apply practical comparison test. We take this as a useful integral. Useful integral for comparison. Comparison test means we require some integral for comparison. Useful integral for comparison. That is integral a to b dx by x minus a raised to n converges if and only n is less than 1. N is less than 1. Similarly, integral a to b dx by b minus x raised to n converges if and only n less than 1. These two are called comparison, they are useful integral for comparisons. Now I prove this in the next video, how a to b dx by x minus a raised to n converges if n less than 1 and b minus x raised to n converges if n less than 1. If n equal to 1 and greater than 1, this does not converge. Equal to 1, greater than 1, this does not converge. Here what is this integral? These two are different. Different in the sense here a is the point of discontinuity, here b is the point of discontinuity. Now using that comparison test and this integral, we can solve many problems. Example, discuss the convergence of 0 to 1 dx by x raised to half 1 plus x square. See the problem here, x raised to half